I want us to take these examples and see if we can solve them. I have some questions here, about 11 of them. We have A, B, C, D, E, F up to K. And of course, if you were to notice, you would find out actually that this limit is actually exactly as just E. If you looked at, I think we had a lecture that was covering the number E. So if you actually looked at that lecture, you'll find out that this limit is actually equal to some E. For now, let me just place a star there. These green questions here, I am not going to cover them in this particular video, but they are part of these exercises. Here is a why. These questions, they require the understanding, not really, but if we are not using the L'Hopital's rule, they become so hard unnecessarily. So the answers to these particular questions, you will find them when we're actually doing L'Hopital's rule. But if you really wanted to find out you wanted to know the answers and you want to do these questions like you're supposed to be, if I give you, let's say, exercises, I want you to pause the video and then do these exercises and see what you are actually getting, and then you look at the answers. Then if you are not getting the answers the same as the one that we're getting here, you look at the explanation. Of course, the solution to this problem, I think, is supposed to be, if I take this and that, this one is supposed to be actually 0, and then this one also is supposed to be 0 because this function is going to increase faster compared to that. So this one is supposed to be 0, and then this one is supposed to be 1. And then if you actually look into this one here, so I say E, and then if you look into this particular question here, you will find out actually that let me double check here, because if I divide by that, this one's going to increase faster than that, and this one's going to increase, and also this one is supposed to be also equal to a 1, and then of course this one is supposed to be equal to e to the power 2. It's not that straightforward, but when you're working on what is inside here, you can actually change it to be in this form, and if this is e, then this is supposed to be e to the power 2. These ones, the solution, like I said, they will be under L'Hopital's rule. When we're doing L'Hopital's rules, we will go back and do these questions here. I want us to do A up to E and see if we understood what we're doing in the previous lecture. And then, of course, if we don't understand, we'll see at a particular stage. You will notice that when we're doing the previous lecture, which was lecture 32, we did not really look much into the summary of how to solve this limit as x approaches infinity. The reason is that I wanted to add the summary after we have done L'Hopital's rule, so that you can see the summary of all the limits and also the limits at infinity. I think it's going to make some perfect sense when we're actually doing that, because after this lesson we will go straight to actually finding the derivatives of functions at some particular point x. So let us start with this one here and see what we are actually going to get if we solve this particular question here. So the first question is supposed to say, let me place this, I have a solution here, so I will have some solutions here. So A is saying that find the limit as x approaches infinity of 2, I don't think so, of 3x cubed and then plus 5x squared and then minus 7 all over a 2x cube minus x and then plus a 4. Now, if you look into this and you plug in here infinity, you will end up having infinite cube, which is infinite times infinite times infinite, which is just infinite. Infinite times 3 is infinity. Plus, and then if you're plugging in here some infinite, you'll get infinite squared, which is the same as infinite. So infinite plus infinite is infinite, and then infinite minus 7 is going to be infinite. And then if you look into this portion over here, you will find out that we have infinite, and then this infinite I will end up having infinite times infinite times infinite, which is just infinite times 2, and then infinite times 2 is infinite. Now we started to have minus infinite, now infinite minus infinite, and of course now that we have infinite minus infinity, we started to have an indeterminate form in the denominator there. Of course, in the numerator we had infinite, so if we were going to get another infinite in the denominator, we were actually going to have another indeterminate form. So in order to remove that indeterminate form, what we actually do here, we try and remove the part that is giving us an indeterminate form, which means that the first thing that we can try to do here is factorize. So when we are factorizing here, we don't just factorize for the sake of factorizing and say we wanted to factorize and get this and factorize this whole thing and factorize that whole thing. We don't do things like that here, because the main thing that is important here, if we are looking at the numerator here, we want to find the function that is actually increasing faster than everything that is there as x increases unboundedly. And also in the denominator, we want to look at that dominating function that is increasing faster than all these functions, so that we can compare those two functions. That is actually why we look at the highest power in the denominator and factor it out first. So the highest power in the denominator is x to the power 3. So we're gonna take out x to the power 3, and then when we're taking x to the power 3, what will remain here is 2x to the power 3 divided by x to the power 3 that we have taken out, and then minus x divided by x to the power 3 plus a 4 divided by x to the power 3. And also we do the same thing in the numerator. We don't just factor, even if this one did not have an x, we want to factor the highest power of the denominator. So this same power in the denominator is what we want to factor out in the numerator, because we want to make sure that we can compare which functions or which term are actually leading in this whole rational function here. And then we end up having 3 to the power 3x to the power 3 divided by this thing which we took in the denominator. So we have that plus 5x squared divided by x cubed minus 7 divided by x cubed. And of course this x cubed and x cubed, they cancel out, and now we're left with the limit as x approaches infinity of this one is gone, x cubed and x cubed are gone, and now you have 3 plus 5 divided, so I have x squared, so I'm gonna take x squared out and we'll be left with 5. And when I'm taking x squared out in x cubed, I will end up with having only 1x, and then minus 7 divided by x to the power 3, and all over, and then here this is gone, x cubed and x cubed, they cancel out, and now we are left with a 2. And then here 1x is there, and now it's gone, I'm left with 1. And then here if I take 1x out, I will be left with 2 of these things here, and then I'm still left with 4 over x cubed. Of course, we are trying to do everything we can to remove the indeterminate form, and now this is going to be 3 plus, and if you look into this, this is going to be 5 over infinity, and then minus 7 over infinity cube, or infinite times infinite times infinite. Infinite cube is going to be infinite times infinity, which is infinite times infinite, which is infinite. So this is the whole thing is going to be an infinity. And then you divide here, and you have a 2 plus 1 over infinite squared, and we know that infinite squared is just infinite times infinity, which is infinity. And then here we're going to end up having 4 over infinite cube, which is the same as infinite. Again, like I explained, that you find out people are scared of plugging infinity or are criticizing this thing of plugging infinity because infinity is a concept, it's not really a number. I always encourage students that when they are still trying to figure out what is this concept of infinity, to plug it in. I know that we are not supposed to be plugging in that thing here. We just have to conceptualize in such a way that we have this x that is so big or is increasing unboundedly, and then want to find out what is the behavior of this function as x approaches that. And you end up jumping this step, and someone is just saying that this is supposed to be just 3 plus 0 minus 0 all over 2 plus 0 plus 0. They jump this step because someone is saying that this function actually is decreasing and decreasing and decreasing closer to become closer and closer to 0 as this gets to 0. But I usually encourage this because this one actually gives you an overview of what is actually happening, to say that actually if I have 5 and I'm dividing by a very big number, the answer that I'm going to get is going to be closer and closer to 0, and then minus, and if I'm dividing 7 by a very big number, we'll get a number that is just closer to 0. The same thing for this one and the same thing for this one. That is why we have 2 plus 0 minus this and that, which is just the same as 3 over 2. So that's what I want students to get familiar with. Of course, once you get to understand this whole thing, you can actually move straight from this and understand the functions that actually this one is decreasing and that one is getting closer and closer to 0, and you skip this whole stage and you come here and then you go there. This step is important and that one is important, and marks wise this one is important and that one is important. And of course, the next step that actually have some marks is this one when you are factorizing, and this one here. This one over here is not that important much, but there are some marks. For me, I usually give some marks when it comes to this because it shows that someone is trying to use the algebra of infinity and 0 to solve these things out, and also they also understand the concept that this one divided by a very big number, you are getting a 0. So I usually put some marks here. Some other people don't want to put marks here because they don't like the idea of plugging infinity, because infinity is not a number, it is actually a concept of a big number. So depending on who is actually asking questions, but the answer, there are marks for this one. Sometimes 2, others prefer to put 1. I prefer to put 2 for actually factoring this out, and also knowing that this you take it from the denominator. So I usually put 1 mark for the numerator and 1 mark for the denominator, 1 mark, numerator 1 mark. And then when it comes to this, I also give 1 mark because you knew that you can actually simplify that. And then when it comes to this one here, I give you 2 marks sometimes if you already simplified this to be infinity, and also simplifying that and that, you usually get some 2 marks, and then 1 mark for this and 1 mark for that, knowing that you know that you can simplify that. Depending on who is setting, of course, people have their own way of doing things. Let's go to B now. And then B is saying that we want to evaluate the limit as x approaches infinity of x squared, and then plus 3x, and then plus 2, all over, I have the square root now of x to the power 4 plus 2x squared plus 1. So if you look carefully into this function here, you will find out actually that we have a root in the denominator. And now if you are trying to find this whole thing, I can plug in infinity, and I know infinity squared is going to be infinity times infinity, which is just infinity, and then plus 3 times infinity is just infinity, and infinity plus infinity is going to be infinity plus a 2. I mean, 2 is insignificant compared to infinity, so I end up having infinity divided by, and here infinite times infinite times infinite times infinity. Of course, these big numbers you still get infinity, and then plus infinity squared is the same as just infinity times 2, which is infinity. So I have infinity plus infinity, that's infinity, plus a 1 is insignificant, so we end up having the square root of infinity. And then the square root of infinity, because that's just a big number, whether you're taking a square root of it and you are squaring it, you're still supposed to get the same infinity. So we end up having infinity over infinity, which is actually this one, which is actually another indeterminate form. So how do we end up removing the part here that is actually going to give us this indeterminate form? What is basically happening here is that the infinity in the denominator is coming from this part here, which is x to the power 4. So it is the one that is actually giving us the infinity in the denominator, because this one is the one that is actually causing us to have this. So we want to remove that infinity in the denominator. It's okay to have infinity in the numerator. If let's say this limit was just infinity, we're still going to say that it is infinity. But now the issue is when we're actually having that infinity in the denominator, or having a 0 in the denominator, given that we already have another infinity there, or a 0 there in the numerator, that's when we start to have a problem. So we wanted to remove that problem that is caused by this part here. So of course, if you wanted to remove that problem, what you need to do, you need to factor out the problem so that you can remove it. So we're still going to have x squared plus 3x plus a 2, and we want to factor out that problem there. Take note that I still have a square root there, and I wanted to have x to the power 4, and then I want to factor it out. So here I will have x to the power 4 divided by x to the power 4, and then plus 2, and then I have x squared divided by x to the power 4, and then I will have 1 divided by x to the power 4. So that's what we actually do here. And then we're going to have the limit as x approaches infinity. And then if we look into this here, we still have x squared plus 3x plus a 2. The thing here is this. Remember that our main goal is to factor out the highest common factor in the denominator and also in the numerator. So if you look into this part here, you'll find out the reason I'm not factoring anything out in the numerator is because I haven't found what to factor out from the denominator. So I want to first factor out from the denominator so that I can factor out in the numerator. So that's what is actually important in this whole thing here. So let's look into this now. This whole thing, I know that it is the same as just the square root of x to the power 4 times the square root of x to the power 4 over x to the power 4 plus 2x squared divided by x to the power 4 plus 1 over x to the power 4. In most cases, when it comes to questions like this of this type, they are more likely to come out, especially if you are not doing the more advanced mathematics. Usually questions of this type, they usually come out a lot. And questions like this, they're a little bit advanced, but still doing the same thing here. So we have the limit as x approaches infinity. And now I'm still gonna keep this because I haven't found from the denominator what to factor out. And then I'm going to simplify what is happening here. In this part here, I want you to notice something here, that the square root of x to the power 4 is the same as the square root of x squared, the whole squared, because this 2 times 2 is going to give you a 4. And of course, if you look into this part here, this is the same as just the absolute value of x squared. Whenever you have the square root and you have the square, you must know that it means the absolute value. So in this particular case here, you will end up having the absolute value of x squared, and then what is inside here, x to the power 4 divided by x to the power 4 is a 1, plus 2x to the power 2 divided by x to the power 4 is just going to be 2 divided by x squared, and then plus 1 over x to the power 4. So just take note of this. Remember that we said that whenever you have the square root of some x squared, this is the absolute value of x. So this one and that one, they actually cancel out to produce this. And also here we need to change this so that it is squared. So we have a 2 here. So we have this and that, they actually end up cancelling, and we are left with this, and now we are getting the absolute value of that. But now what I want you to notice here is very simple, is that whenever you have this thing here, this absolute value is there to make sure that the answer that you are getting out of this is positive. Because the absolute the x squared is always positive, then having this thing is not going to change anything, because x squared is always positive. So we are actually having x squared plus 3x plus 2 all over x squared times 1 plus 2 over x squared plus 1 over x to the power 4. And now I can see that this x squared is the one actually that was causing the denominator to have infinity. So this is the leading factor in the denominator. So I wanted to find to actually factor out the very same thing that is in the denominator in the numerator. So I end up having the limit as x approaches infinity. I'm gonna factor out x squared because I want to cancel this infinity over infinity, so that I end up getting something that is actually determinate. So inside I will end up having x squared divided by x squared plus 3x divided by x squared plus 2 divided by x squared all over x squared times the root of 1 plus 2 over x squared plus 1 over x to the power 4. And if we proceed here, we will end up having something nice like x approaches infinity, and then this one will cancel with that, and this one and that will end up being a 1 plus 3 divided, because this x will be gone and one of these x will be gone, and now we'll be left with 1x plus 2 divided by x squared all over the square root of 1 plus 2 over x squared plus 1 over x to the power 4. Now, taking this into account that we have removed the infinity over infinity, now we want to plug in. So when we're plugging in, we drop the limit. So we end up having 1 plus 3 over infinity plus 2 over infinity squared, and then all over the square root of 1 plus 2 over infinity squared plus 1 over infinity to the power 4. Now we know that infinity squared is the same as infinity times infinity, and infinity times infinity is just infinity. And we also know that, so this part here will be the same as infinity, and this part will be the same as infinity, and infinity to the power 4 is the same as infinity squared times infinity squared, which is just the same as infinity. This was infinity, infinity times infinity is infinity, and then this one is also infinity, which is the same as infinity. So we know that this part here is just equal to infinity, and this one here is just infinity, and this one here is just infinity. And then now that we have that, we can see that this whole thing will end up being 1 plus 3 over infinity. We know that infinity is so big compared to that, so that will actually go to 0, plus, and then infinity is so big compared to 2, so it will go to 0, and then in the denominator we end up having the square root of 1 plus, and infinity is so big compared to that, so we end up having a 0 plus 0, which is equal to 1 divided by square root of 1. We know that the square root is always positive, so we end up having the final answer as 1. So that is actually one thing that is more important, why the square root is always positive. Just keep note that one mistake of making a sign here, you usually get penalized, but make sure that you don't make a mistake of a sign. That's what is important when it comes to this. Let's go to number C. Number C is evaluate the limit as x approaches infinity of the square root of x squared plus 3x minus x. So if you look into this equation here, you will see that if we can plug in here infinity, we'll get infinity squared, which is infinity, plus 3 times infinity, which is infinity. So infinity plus infinity is infinity, and the square root of infinity is infinity, and then minus infinity. So I have infinity minus infinity, which is also an indeterminate form. So I wanted to convert this so that it does not have an infinity minus infinity. I want to convert this to a determinate form. And in order for us to convert this to a determinate form, what we need to do here, we need to actually factorize like we were doing up here. We wanted to factorize. Take a look in number 1 that we just factorized the highest power in the denominator, and then when it came to this one here, we actually found out that the highest power is x cubed. And then in the second one, we find out actually we know that this is the highest power but is inside the root. The first thing, we wanted to take it out and see what is the exact power, and then we worked with it like this, and then we ended up finding that actually x squared is the highest power, and then we started to factorize here. So we worked with the denominator. So the main thing here is we want to factorize, right? But if you look into this here, we can't factorize when we have a root here. So the first thing that we want to make sure of, we want to remove this root so that we can factorize, so that we can end up having maybe infinity times infinity. That's the main goal of factorizing a limit of this type. We want to end up having either an infinity over infinity, infinity times infinity, which we know that it will be infinity. And then secondly, we want to either get a 0 times 0, which we know that it is 0. That's why we are converting this. Or we want to get infinity over infinity, or 0 over 0, because we know that if we are falling in these two, we can always use L'Hopital's rule. We can factorize, we can rationalize, we can use L'Hopital's rule if we are facing this, but L'Hopital's rule is always powerful, as I've said. Now, we want to remove this root so that we can be able to factorize to get something of this, or manipulate whatever is here to get anything of this type here. Take note that this is also indeterminate form, but this indeterminate form can actually be solved using L'Hopital's rule. That is why I'm saying converting something to this is actually of advantage, because we can do something. But here we have this root here. But another thing that I want you to notice here is this. This is actually a nice function that is divided by 1. So if that function is actually divided by 1, the only way to remove a root so that we can gain 1x so that we can factorize. Take note of this. Once this root, if this root was not there, we can remove 1x here, 1x there, and this 1x, so that we end up having x, and then we have some x something inside minus 1. And of course, if this one is infinity, I will end up having infinity minus 1, and minus 1 is so insignificant compared to infinity. So we end up getting infinity over infinity. So how do we end up converting so that we can factor something out? So the first thing that you actually do here, you rationalize to remove this. So I had x squared plus 3x minus x divided by 1. Now, if I rationalize the denominator here, this denominator is not going to help us to remove that root. so that we can take 1x out to factorize. So I need to rationalize the part that have something that we need to remove. So we rationalize this whole thing. And the part, the square root, we have a square root here. So anything that is inside this square root here, so the square root of that something, we call it one term, and then the remaining part is another term. In other words, here, even though we have x squared and 3x and then we have x, the numerator does not have 3 terms, it have only 2, because the square root contains everything inside, so we consider as one term, because we want to remove that one square root and that. So to rationalize, we multiply by the conjugate, so we change the sign that is between this term and that last term. So we're still gonna have x squared plus 3x, and then we have a plus x now, because this thing was not part of this, so we have to divide by it again. So we end up having x squared plus 3x plus an x. Again, whatever was inside the denominator there, I'm not going to simplify because I wanted to cancel something that can be cancelled. That is why I'm not going to simplify. I am only going to simplify the numerator because it contains the x that I want to factor out if possible. So I end up having the limit as x approaches infinity of I'm gonna end up, if you look into this whole thing here, I will end up having the square root of x squared plus 3x times this whole thing here. It's always good to put the brackets so that you don't make mistake. So I'm gonna multiply this with that, so that's the first part. So I'm going to square it up, and then I'm gonna multiply this with that, so I will end up having a plus x times the square root of x squared plus 3x. So plus and a plus, so it's a positive, and then now I'm gonna multiply, we have a negative, so minus x times the square root of x squared plus 3x. So this minus plus a plus times a plus is going to be negative, and then I have that whole thing, and then I have a minus and a plus, so I have a minus. Minus times positive is minus, and then I have x times x, which is going to be an x squared. I divide this whole thing by what is happening in the denominator. I'm not going to simplify what is in the denominator because if there was something to cancel there, I want to find it still waiting for me there. And if you look into this part here and this part, they are the same except that the sign are different. So this part and that part is gone. So I end up having the limit as x approaches infinity of the square root of x squared plus 3x, and then I'm gonna square it up, and then minus x squared all over the square root of x squared plus 3x, and then I have plus x there. Now let's take a note on this thing here. If you take a look into this, I want you to notice something here, that here I have a square. Since I have a square here, a square will remove this root here, so I will end up having the limit as x approaches infinity of x squared plus 3x minus x squared all over I have the square root of x squared plus 3x plus an x. I want to emphasize something here. Hopefully it's not going to confuse you. Whenever you have the square root of x squared, this is the same as the absolute value of x. It doesn't mean that this has to cancel this whole thing, but whenever you have the square root of x squared and then the square root of x, and now you have a square, this one is going to cancel that, and now you end up having an x. These two things are different because this one here is actually going to actually give you something that is actually it can either be, if you want to rewrite this, we know the answer is supposed to be always positive, and of course if you look into that, you will end up having this. I want you to notice that whenever I'm talking about this case here and I end up not having an absolute value, it doesn't mean that we should always get an absolute value of this thing here, because that one is just gonna take it out, right? It's just gonna take out whatever that was. So we're still gonna get exactly what was inside there, because this is just gonna take it out. But when it comes to this, we not guaranteed. That is why we end up having an absolute value. So let's hope that is not confusing you, or you actually understand what is basically going on here. And if you look into this now, you can see that I have an x squared and an x squared, but the sign, this is negative, that is positive, so it's actually gonna go away, and we end up having x approaches infinity of just 3x all over the square root of x squared plus 3x and then plus some x there. Now if I am plugging in here infinity, 3 times infinity is going to be infinity, and I'm plugging infinity, I will get infinity over infinity. I am actually getting now infinity over infinity, which is actually saying that converting this, we have converted this indeterminate form to actually another indeterminate form. But now the good news is this: because we are having infinity over infinity, we can directly use L'Hopital's rule. We can directly use L'Hopital's rule here. But because we haven't yet studied L'Hopital's rule, then what we need to actually do here, we need to find the highest power in the denominator, so that we can actually want to factor it out, so that we can actually cancel out that part that is giving this infinity in the denominator. So basically we'll end up having the limit as x approaches infinity, and then what is the highest power in the denominator. I'm gonna leave this 3x there because I still want to find the highest power in the denominator. Is this gonna be this x, or is this gonna be this x squared? I don't know what the hell is going on here, but in order for us to find out what is exactly going on there, we actually have to find out what is we want to factorize inside here the highest power and get it out of the root and see what are we actually getting. So inside the square root, I know that x squared is the highest, so I'm going to factor out x squared, and then inside I will end up having x squared divided by x squared plus 3x divided by x squared. And then of course I still have that plus x here, because I'm still figuring out what is the highest power that is in the denominator, so that I can factor out in the numerator and cancel it out and see what I'm actually getting. So here I will end up having 3x, and then in the denominator I still have this. I'm gonna split it to be x squared like this, and then inside I will end up having this x squared divided by x squared plus 3x divided by x squared, and then plus that x there. I am still trying to figure out what is the highest power in the denominator. That's what we are doing here. So we end up having 3x, and then in the denominator, what is this thing here? We know that the square root of the square is just supposed to be the same as the absolute value of x, and then here I have to multiply this whole thing. I have to divide this whole thing. So here x squared divided by x squared is just a 1. 3x divided by x, this x will be gone, and then we'll be left with 3 divided by 1x, because 1x will cancel out, and then I still have plus x there. What I want us to actually realize here, this is important more than anything we have done. We know that the absolute value of x is always going to be x if x is greater than 0, greater than or equal to 0, and it's going to be minus x if x is less than a 0. Why is that so? Is because the absolute value is always positive. So if I'm looking for the absolute value of 2, I know that 2 is bigger than 0. This is supposed to be just x, or just what is inside, so is equal to 2. But if I'm looking for the absolute value of minus 2, I know that this one is less than 0, so it's supposed to be, I have to place a minus first, and then x is what was inside, so I'm going to have minus 2. So this is also going to be minus times minus is going to be a 2, because the final answer of the root is of the absolute value is supposed to be positive. So we need that minus to cancel out that minus that was inside, so that we get a positive. But the main goal of what I'm trying to do here with this definition is this. If you look at x, as x approaches infinity, you will find out actually that infinity here is a very positive number. So it's a very big number, because x is increasing unboundedly. So this one is positive, which means that this absolute value here is just gonna be our x. So we have the limit as x approaches infinity of 3x divided by this absolute value is just gonna take that, because infinity is bigger than or equal to 0, so it's going to be the same as x. So we have x times the square root of 1 plus 3 over x, and then plus x there. Now we can just indulge and then factorize, because we can see that the highest power in the denominator is x. So we'll end up having something nice like I have 3x, and then I factor out x in the numerator, and then I'll be left with the 3, and then in the denominator I factor out x, and then I will end up having the square root of 1 plus 3 over x, and then here I'll end up having a 1 because 1x is gone. So now that we have that, this x and that x, they cancel out, and now you have the limit as x approaches infinity of 3 divided by the square root of 1 plus 3 over x, and then you add a 1 there, and I can just plug in now. And when I'm plugging in, I drop the limit, so I'll end up having 3 divided by the square root of 1 plus 3 over infinity, and then plus 1 here, which is the same as 3. And we know that 3 is so small compared to infinity, so infinity is just gonna say, you're so small to me, let me just round you off to 0. So this is going to be the square root of 1 plus 0 plus 1 here, which is this, which came from that part, which came from factorizing x out here. So I took 1x to get that, so this is the one that we're actually having here, which is the same as 3 divided by the square root of 1 plus 1. And we know that the square root is always positive, so we are going to have 3 divided by 1 plus 1, or we're going to have 3 over 2. You can see how easy this thing is. It's all about converting the indeterminate form to a determinate form. So we're dealing with example number C. Let's go to example number D now. What was actually example number D? If we look at example number D here, you will find out we're trying to evaluate the limit as x approaches infinity of 2x squared plus 3 all over x squared minus 5x plus a 7. And then here we end up having 1 over x. So we had this nice thing here. Now, if you look into this limit here, you will find out that the first thing that we need to do here, if we can plug in here, you will find out that we will get infinite squared, which is infinity times infinity, so it is infinity, and infinity times 2 is going to be infinity. Adding a 3 to it, we're still gonna get infinity, because infinity is so bigger compared to this 3, or 3 is so insignificant compared to infinity. So in the numerator, we'll end up having infinity. And then when it comes to the denominator, we'll end up having infinity times infinity, which is infinity minus infinity. So we have an indeterminate form in the denominator also. But if we can try and complete the square in the denominator, we'll find out actually we will end up with infinity in the denominator by just finding completing the square of the denominator. We'll get infinite. So we have infinite over infinity, and infinite over infinity is an indeterminate form on its own. But now when I'm plugging infinity here, I will get 1 over infinity, which is 0. So I have infinite raised to a 0 there. So that's also another indeterminate form. We don't have a problem of having infinite over infinity, but the issue now is when we are actually having a 0 there in the exponent, because now it's giving a very complicated calculations here. So when we were doing laws of growth and decay, and also the change of bases, there is one thing that I kept emphasizing here, that whenever I have ln of e to the power x, ln is going to actually say that this is the same as just x, because I'm gonna bring this one down here, and then after bringing this one down here, we will actually end up having ln e, which is 1. So this is just saying that ln and e, they cancel each other. And also another thing here, let me just write this so that you can see everything. So we said ln of e to the power x, which will be just x ln of e, is just gonna be this, because this is 1, so you end up having an x. In other words, ln and e, they cancel out, so that this exponent is just there. And another thing that we emphasized is that whenever I have e raised to ln of x, we said that this is just the same as having e raised to log base e of x, because ln is the same as log e. So log base e, and this e here, as long as this number is the same as the base, we said that this and this will undo each other. In other words, e, this whole thing will just be the same as x. So e and ln, they undo each other, so that what is inside is there. And also, even if you do it like this, you're still gonna be arriving to the same thing. So to bring down that exponent, so we want to bring that exponent without changing this limit here. So we either gonna use that, or we're gonna use this one here, depending on what will actually give us a solution. I have to be honest about this, because most people and students usually say that, how do you know that you are actually supposed to choose this one or that one? Once you start choosing this one and you're getting stuck, try and change and use this one and see what you're actually getting, because sometimes when you're using this one, your calculations are easy. Sometimes when you're using this one, your calculations are easy. But the main point that you need to understand here, we want to bring down this exponent there. So if you look into this, we are going to say the limit as x approaches infinity. I'm gonna say this whole thing here and say that I'm just gonna put in e and then use ln, because I don't want to change this whole thing. Ln and e, they will undo each other, and then I'm still gonna have 2 times x squared plus 3 all over x squared minus 5x plus a 7, and then raised to 1 over x, and then I can close here. And another thing you have to notice, that whenever you have a ln here, a ln or any log function, as long as here you have a log or ln, you can always take this down in front. The exponent can be always brought in front or just outside at the ln. So this is going to be the limit as x approaches infinity of e raised to 1 over x, and then times ln of 2x squared plus 3 all over x squared minus 5x plus 7. Now, we have something nice here. Another thing we talked about, if you remember when we were doing continuity, we said that as long as I know I have a function f and f is continuous at the point of interest and I know the limit of what is inside, I can always jump the function and first find the limit. Let me write what I'm saying here. What we said that there was a theorem that we did, and we said that if a function f is continuous at b, and the limit as x approaches some value a of g of x is equal to b, then the limit as x approaches a of f of g of x is just gonna be the same as f of b. That's what we said. So if you look into this here, as long as you know that this function here that is outside is continuous at this point here, you can always jump and find the limit inside. In other words, the limit, if you know that this is continuous as x approaches a of f of g of x, is just the same as f of the limit as x approaches a of g of x. So you can just take the limit of what is inside if you know what is outside is actually continuous. So if we look into this exponential function here, the function f of x is equal to e to the power x. We know that this function here, its domain is just x is an element of real numbers. In other words, this function is continuous everywhere because, it is defined everywhere and you can plot it throughout. It is nicely plotted like this. So this function here is going to be continuous at infinity. So which means that I can just jump this e and take the limit of what is happening in the exponent there. So here, let me rewrite what is up there. The limit as x approaches infinity of e raised to 1 over x times the ln of 2x squared plus it was 2x squared plus 3 all over x squared minus 5x plus a 7. So we had something like this. Let me just double check here. So we had something of this nature here. Now, because I know that the function e to the power x is actually continuous everywhere, therefore, I can just say that this is going to be e raised to the limit as x approaches infinity of 1 over x times ln of 2x squared plus 3 over x squared minus 5x plus a 7. Right. And also another thing here that is much more important is that I have a product of two functions. As long as the limit of this exists as x approaches infinity and the limit of that exists as x approaches infinity, we are actually good to go. One thing that I want you to notice here is that if when I'm taking the limit of this and the limit of that separately, I end up getting 0 times infinity, the method we used is not working because now we're actually getting another indeterminate form. We need to change the method, or we need to change ln and start with e, or find another technique if we're getting stuck there. Right, that's what I wanted to mention here. Because most of the time when you are actually solving these limits, you'll find out you're actually moving to another indeterminate form and you don't know what to do. You just need to change, especially now that you don't know L'Hopital's rule, so you really need to change. But if you know L'Hopital's rule, things will actually be way too easy for you to solve. Now, this one is going to be the same as the limit as x approaches infinity. Because I have a product of two functions, I'm going to take the limit of this function here and then multiply by the limit of the other function and then I multiply I take the product of these two functions. This is supposed to be ln of 2x squared plus 3 over x squared minus 5x plus 7. Now, another thing that I want us to actually remember here, I have the limit as x approaches infinity of 1 over x times this function here. You know that ln is a function that grows like this and is only not continuous when x is equal to 0, but after that is always continuous, and at infinity ln is always continuous. So I can jump ln and take the limit first, and then after taking the limit I take ln. So here I will end up having ln of the limit as x approaches infinity of 2x squared plus 3 all over x squared minus 5x plus 7. So if you look at this particular equation here, you will find out actually that I know the limit of this because I can just have my e there, and then I plug in here to get 1 over this is not infinity, it's 8. 1 over infinity, and then times ln of whatever is inside there. Take note that once I have a limit of a function of this kind, of a rational function, I want to find out what is the leading term in the denominator so that I can also factor it in the numerator. So I'm still gonna have the limit as x approaches infinity of, and then in the denominator x squared is leading, so I'm going to factor out x squared. Once I factor x squared, I will get x squared here divided by x squared, so that this and that cancels out and we get that, minus 5x divided by x squared, and then plus 7 over x squared, right? And then in the numerator, we'll do the same thing, factor out an x squared, which was from the denominator. And then I'm going to end up having 2x squared divided by x squared plus 3 divided by x squared. And then I'm closing this whole thing for the ln. And now I end up having e. If you look at 1 is a constant. Any constant divided by infinity, you are going to get a 0, my dear. So this one here, you end up having a 0 times ln, right? This is a natural log. What is going to be inside? This one here and that will cancel out. I still have a limit as x approaches infinity. And then this x squared and that x squared will cancel out. And now I will end up having a 2 there. And then plus 3 over x squared. And then this one here, x squared divided by x squared is just 1, minus 5 divided by x, because 1x will be gone and 1x will be gone there. And then here I still have 7 divided by x squared. I know that it is tempting to just say, because I have a 0 here, anything multiplied by 0 is going to be a 0. When we are dealing with infinity, always be careful, because 0 times infinity is actually not 0, it's an indeterminate form. So we want to first find out if this thing is actually not going to give us an infinity, a positive infinity or negative infinity. If it's giving us a positive infinity or negative infinity, whatever we have been doing here is actually not worth it. We need to try another method, because we are actually having a 0 times infinity. Or if we already know L'Hopital's rule, we can convert 0 times infinity to infinite over infinite and then use L'Hopital's rule. That's what is nice about this whole thing. And then now that we have this thing, this is always gonna be e times 0 times this one here is just gonna be, we still are gonna have ln, and then here I will have a 2 in the numerator, and then I'm plugging in, so I drop the limit, so I will end up having 3 divided by infinite squared all over 1 minus 5 over infinity plus 7 over infinite squared. And this is going to be equal to e raised to 0 times ln. And if you look into this here, infinite squared is infinite times infinity, which is just infinity. So 3 divided by infinity is going to be 0, so we have 2 plus 0. And also here I will have 1 minus 5 is a constant. Constant divided by infinity is always going to be 0. Constant divided by infinite squared, which is infinite times infinity, which is infinity. So 7 divided by infinity is still going, because 7 is a constant, it's always going to be 0, which means now we are actually having e raised to 0 times ln of 2 divided by 1, which is just e raised to equal to 0 times ln of 2. And we know that ln of 2 is a value. You can even check it here. Ln of 2 is actually a nice value, which is 0, something something. So basically this is a constant. Any constant times 0 is just 0, so we end up having e raised to 0, which is just a 1. So all we were calculating, we were just trying to get a 1 there. So that's how we actually solve this particular problem. Let us look for the last one here, which is e, and then we can call it a day. So this one was saying that evaluate the limit as x approaches infinity of I think it was x cube plus x times sine of x all over, and then I'm gonna end up dividing by x cube. I think that was it. Yeah, if it's not it, you can always, I think you will be able to do it. It's of the same type here. So looking into this limit, this one is very, very, very straightforward, because we are looking for the leading term in the denominator so that we can compare with the numerator. Now what we are going to do here is that in the numerator I have only one term, which is x cube. So I want to factor x cube in the numerator there, so I will end up having x cube, and then here I will end up having x cube divided by x cube to find out what will remain, plus x times sine of x divided by x cube. And this whole thing I'm gonna divide by x cube. X cube is there, so there's nothing to factorize because it's the only factor that is there. And then we're gonna have this whole thing, this one and that, they cancel out, and x cube divided by x cube is just gonna be 1 plus. And then if you look into this part here, you will actually find out that we are actually having this one x will be gone and one of the x's will be gone there. Now we end up having sine of x divided by x squared. All right, and if you look carefully into this, we try and plug in here. So if we're plugging in the value of x infinity, we'll get 1 plus sine of infinity divided by infinite squared. And you know that actually infinite, this is still infinity, and we know that infinity is the same as infinity times infinity squared, and this is just infinity. So if you look carefully into this, we know that sine of anything is always a value that is between -1 and +1. So I'm gonna call that value m. It is a constant m. It can be -1, but I know that this value here is actually between -1 and +1. And having this infinity times infinity, we know that it is infinity. So whatever that constant is, I don't care whether it's positive or negative, but one thing that I know, it is a constant that is so small compared to infinity. So this whole thing actually it will go to 0 because this one is so small compared to that. So this limit here is actually equal to 1 plus 0, which is just equal to 1. I hope that these examples or these exercises have enlightened you how you can actually change an indeterminate form to a determinate form. So that's what is important. After we have done L'Hopital's rule, you will see actually when we are solving f, g, h, and all these other problems, that's when we'll be solving them using L'Hopital's rule. And then after L'Hopital's rule, that's when we'll also summarize on how you can actually solve this particular how you can solve limits, right? The summary of solving limits, especially those one that has to do with x approaches infinite. I think we will end there for today.